Okay, so today Dmitry Golubenko continues his talk about tensor algebras of C-star correspondences and their C-star envelopes.
Okay, thank you. First, let me remind some notions I have introduced earlier. So first of all, we work with C-star correspondences, which are just Hilbert modules. It's just with some form from E to E to A, some C-star algebra, such that this form satisfies the following conditions. And it is also non-negative. And also it is equals to 0 if xi is 0. So, well, and we also have function phi from A to linear operators on E, which gives us a left action of C-star algebra A on C correspondence E. What we are interested in, we are interested in calculating C-star envelope of tensor algebra of E. So tensor algebra, let me also remind, having E, we may define its tensor degree, and also zeroth degree is just A. Having said that, we may define Fock space, which is a direct sum of these degrees, and then define creating operators and angulating operators and diagonals phi infinity by the following. So we define for every xi from C-star correspondence E, we may define.
Dima, I'm sorry, we cannot see the whole page. So could thank you.
Which is x on xi by just multiplying on xi, and this operator acts from nth degree to n plus first. So also we define txc and dual as actually dual operator, and also we define phi infinity acting on A. So phi infinity is just from A to an operator on to this operator. So we define it to be this infinite infinite matrix, which acts on A by multiplying on A, acts on first degree by phi of A, acts on the second degree by phi of A, and so on. Then we define its tensor algebra as a norm closed algebra generated by Txi and phi infinity of A. And what we're interested in, we are interested in computing C star envelope of T plus of E for some C correspondences E. So now for C correspondence, we have this. We actually have two algebras, A and B. B is C star algebra, and A is some operator algebra, and A generates B as C star algebra. Then we may consider its C star envelope of A as some universal C star algebra generated by A, which in some way encodes representations of A. To be more specific, I say that E is a boundary ideal if the quotient image from B to B factor G is an isometry, complete isometry, when limited to A. And now, from all of the boundary ideals, we may consider the maximal one, and the maximal boundary ideals is called Shilov ideal. And thus, we may consider factor B to Shilov ideal. There is unique unique Shilov ideal in B related to A, and B factor G is C star envelope of A in B. And now I would like to compute C star of T of E for some simple cases. Okay, first of all, I need some propositions. To prove this one. So first, let me give some more definitions. As I have phi and E, so let me take K of E as an ideal of compact operators. And let me define relative Kunz-Pimsner algebra related to some ideal G0. So, so let me take an ideal in pre-image of compact operators on E by the image phi. And then I may define this G beautiful of G0 as an ideal generated by phi infinity of G0 P0 in tensor algebra. Here P0 is a projector on some first summons. Actually, P0 projects the whole sum onto E0 equals A. And my proposition is let E be a strict C star correspondence over A. And G0 is an ideal such that it doesn't intersect the kernel of phi, so such that then this ideal G beautiful of G0 is a boundary ideal in tensor algebra of E for T plus of E. And so it follows that C star envelope is a factor of this relative Kunz-Pisner algebra. Everything's clear now. Or not?
Could you remind what is strict correspondence?
Okay, so the last time I was talking about topology, I would like to define on C star correspondence. And I didn't say it quite clearly, but strict C star correspondence is a C star correspondence endowed with such topology. So if we have I try to define some kind of strong star topology on E. And with these topologies, I have defined E as a strict C star correspondence. In our case, E will be finite dimensional, so it would apply automatically. So so let me also remind, I have defined also disk algebra and non-commutative disk algebra, and in those cases A was equal to C and E was finite dimensional. And in these cases, this was these lemmas will actually work out. So E will be automatically strict. So okay, now before I would like to prove this proposition, I would have to prove another theorem, which is this. Do I have to remind what is a coherent representation is? Мне нужно это напоминать или нет? Что такое ковариантное представление? Anyone? Okay. So let me again remind what is covariant representation. Well, as I have E, which is C star correspondence, and Gilbert space H, I will introduce the pair V and sigma as covariant representation of E on H, some H Gilbert space. If V is an image from E to bounded operators on H, and sigma is also a map from A, C star algebra, to bounded operators of H, such that they respect each other in the way that T of XA, V of XA is V of X times sigma of A. Okay. So the following lemma is this. Suppose that E is a strict C star correspondence such that some ideal G0 doesn't intersect with kernel of phi. And let also V sigma be a completely contractive covariant representation of E. Then there exists some Gilbert space H tilde containing H, and some G0 coisometric completely contractive covariant representation U rho on H tilde, which essentially extends representation V sigma, so rho of A limited on H is So I will just formulate this lemma. I wouldn't like to prove it thoroughly. I'll just formulate this and its consequence. So I'm sorry. For its corollary, I will use first one. So let T sigma be a G0 isometric, completely contractive covariant representation of E on H. And let also VP be a minimal isometric dilation of T sigma. This stands actually that I can find two operators such that I can write T limited on but I can write T as okay, sigma P, I'm sorry, P of A as sigma V star sigma of A V. So I just take some left uppermost corner in some sense, and so if we have this, then VP is G0 coisometric. And also the following theorem I will use to prove why my first proposition is this. So if E is a strict C-star correspondence over A, and G0 is an ideal which doesn't intersect with kernel of phi. Then every completely contractive covariant representation has a dilation that is both isometric and G0 isometric. Now we will use the theorem to prove our proposition. So that our G beautiful of G0 is a boundary ideal in the Toplitz algebra for tensor algebra. So okay, let us consider the quotient map from simplex algebra to this sorry, to this relative Kuhn-Spinzer algebra. So it is actually a factor of, as I said, T of E factor by this ideal phi infinity of G0 okay. Now we would like to prove that Q bounded to tensor algebra is complete isometry. It is sufficient to fix a matrix. No, some n time n matrix. And to prove that its norm is not decreased by this factor image. Okay, let us fix such matrix and choose the symmetric coherent representation. So fix matrix, then choose such that these norms are equal. Such P exists because every representation of n by n matrices on T plus of E is unitarily equivalent to a representation of this form. So moreover, we may take P that such P is integrated. So P could be presented as sigma times V. We also discussed what is integrated form of coherent representation the last time. Integrated form of representation exists, is unique, so such P also exists, and every representation is unitarily equivalent to representation of such form. And so, as this P exists, we may find a dilation which is isometric and G0 coisometric. Now we have that P tilde actually, which is integrated form of this representation. P0 actually annihilates this ideal. we have the following inequality, which actually by definition equals which is no less than norm of dilation, which is no less than the norm of Q of AIG. Okay. Anyone is here? May I follow?
Yes, we hear.
Yes, please. Go ahead.
Thank you. Так. Now, as we have boundary ideals, we may define boundary representation. Okay. That's definition. So we have A, B, which A is operator algebra, B is C star algebra, and let P be an irreducible C star representation of B. So we define P is from so P is boundary if there is unique completely positive map from B to bound operators on H, such that P agrees with this map. Okay. We don't know if the boundary representation exists in general case, but in our case they do exist and they're easily computable. So let B be a C star algebra. A is contained in B. A generates B as algebra. And also let rho be a completely contractive representation of A. Then a restriction of rho to A is so rho. So I'm sorry. So then rho is a restriction of boundary representation to A from B. If and only if H rho is irreducible and orthoprojective and orthoinjective. I will not prove ortho-injective and ortho-injective. I will prove irreducibility, which is quite simple. So if rho is a restriction, then we have that H rho is isomorphic to H of P, and rho of A equals P of A. And as P is irreducible, so H rho is irreducible. And if H rho is orthoprojective and then H rho is so okay. So yes, so now rho is restriction to A of some representation P. So there exists some P such that P restricted to A is rho. And as P was reducible, then rho would be also reducible. So H rho is reducible, and P is a boundary representation. Okay. And now I would like to define an orthoprojective module of a tensor algebra of E, and show how these Gilbert modules of T plus E are connected with contractive isometric representations of E by the following theorem. So let E be a strict stack correspondence over C star algebra A, and T sigma is completely contractive coherent representation of E on H. Then if kernel phi is contained in kernel of sigma and map from to sigma of A is continuous, then T sigma is fully isometric if and only if in this integrated representation ortho-injective. And the second, so suppose that G0 of A is an ideal contained in preimage of compact operators, which does it intersect the kernel and such that the closure of phi of G0 or on E generates E. So I say that it generates the whole E and also is dense in E. Then T sigma is G0 isometric if this integrated representation is ortho-injective. Now, let me prove the first part. Okay, so suppose that okay, so suppose that sigma times T is not ortho-injective. This exactly means that we have a Gilbert representation for yes, Gilbert space H and contain H1 containing H. And completely contractive representation of tensor algebra such that rho 1 leaves H invariant, but if rho 1 would be written in disintegrated form, we would obtain a completely contractive covariant representation T1 sigma 1 such that T1 acts on H1 as follows. So let me write H1 as H plus it's H orthogonal in H1, and here T1 acts by this upper triangular operator. And sigma x diagonally. So here C is from E, and A is an element of C-star algebra. And also, and the major point that this element is non-zero. And thus, our our representation is not fully isometric. So, on the other hand, if T sigma is not isometric, we may also consider some Gilbert space H1 as H plus some H stroke, where and also extend covariant representation of H. We may also extend it to a covariant representation T1 sigma 1 of H1, where T1 also acts by some non-trivial upper triangular matrix, where dx is also non-zero. So if I consider its integrated form, I'm sorry, it extends sigma times T and is also not ortho-injective. And the second part is proved the similar way. I will omit the proof actually, but it's done the similar way. And now the major statement about C star envelope, which works for disk algebras, but not only for them. So let E be a strict C star correspondence over A. So if E is a faithful left A module, then a C star envelope of tensor algebra is a quotient of Kunz-Pimsner algebra. And the second is if G is an ideal we discussed before, so such ideal that contains in preimage of complex operators, such that it doesn't intersect with kernel, and is dense in E and generates E as module, then its C star envelope is the relative Kunz-Pimsner algebra we defined before. And let us concentrate to the proof of the second part. As we know from the very first lemma, G0, G beautiful of G0, is boundary. And we also need to prove that every reducible representation is boundary. So we know this, and we'll now prove that. Okay. So if P is if this integrated representation is irreducible, then it is ortho-injective. I will prove this a bit later. And also, we conclude that this representation is G0 isometric. And thus, we find out that restriction of P to tensor algebra is also ortho-injective. And then we may use the theorem as a criterion for boundary representation. And thus we have that restriction of P on tensor algebra is ortho-injective and also coincides with some representation which is boundary. So P is boundary, and thus relative Kunz-Pimsner algebra is a C-star envelope. Now, let me prove the ortho-injectivity. So, okay. Now, let me define the Shilov representation, which is this. So I call, I also have A in B and so on. So algebra, operator algebra. And then I will define I will call representation a Shilov representation. And R sigma is relative to B, and is R sigma is a Shilov module of A relative to B. If there is some C star representation of B, and some subspace in HP invariant under P of A. Such that representation sigma is unitarily equivalent to the representation given by this formula, which is sigma of S beautiful is actually a restriction of P of A to S beautiful. And a Shilov representation relative to C star of A will be simply called a Shilov representation. Okay. Now, so the statement I would like to prove is this. If E is a C star correspondence, or a C star algebra, then every Shilov module T plus of E relative to T of E is strongly orthogonally projective. So, okay, now let us follow. So, the first statement is this. If E is a C star correspondence, then representation then yes, then representation of T plus of E is Shilov relative to Toeplitz algebra. If its associated covariant representation of E is isometric. And if if covariant representation is isometric, then its integrated form is a C star representation of Toeplitz algebra on H, and is also Shilov. And conversely, if we have a Shilov representation, we may consider its disintegrated form. So if rho is if it's Shilov, it is some rho times me, and we may consider its disintegrated form, and it will be isometric thus теорема is proven. And now maybe the last proposition. So let E be a C star correspondence. And let rho be a completely contractive representation of its tensor algebra. Then H rho is orthoprojective if H rho is Shilov relative to T of E. Okay, if so to prove, I have to take in mind that if rho H rho is orthoprojective, then it is Shilov so relative to C star of T of E. And since this C star algebra is a quotient of Toeplitz algebra T of E, Thus, H rho is relative to T of E. And if H rho is not orthoprojective, then I can extend this representation with some lower triangle representation, which means I have this covariant representation of some K containing H such that T1 may be expressed the following way. And this D of Xi is non-zero. And thus, if we have this D, we may actually figure out that its dilation and the corresponding operator is also non-zero. So if we have D, we may define D tilde by this formula. And this D tilde is also non-zero. So let us also use a projection from related tensor products of K to tensor products of H and compute this expression. This actually follows from this definition of T1. And thus, I may conclude that Q T1 star T1 Q is T tilde star T tilde plus D tilde star D tilde which is actually larger than equal than q t tilde star t tilde q. And since t tilde is not zero, the inequality is strict, and we may find out that q t tilde star t tilde q is less than equal than q, and thus t tilde star t tilde is less than identical operator and is not equal to it. So T sigma is not isometry. And thus, as this is not isometry, then its correspondent module H-rho is not Shilov.
Dima, I'm sorry, we cannot see the whole page. Thanks.
And its immediate corollary is that if is a C star correspondence of a C star algebra A, then every Shilov module with respect to surface algebra T of E is also Shilov with respect to C star of tensor algebra, and also orthoprojective. And from this corollary, we actually conclude that every Shilov module for tensor algebra is relative to Toeplitz algebra is strongly orthogonally projective, which leads us to our calculation of C star envelope. And I have about several minutes, yes?
Yes, 3 minutes.
Okay, so it is quite enough to say what all of this has to non-commutative disk algebras. Okay, so uncommutative disk algebra, which is actually it's a partial case. Well, now we have A is actually equal to C, and the correspondence E is Gilbert space over C, and it's just some n-dimensional space, and non-commutative disk algebra AN is tensor algebra in this case. And these G small, which is a pre-image of compact operators, is just C here for finite n, and 0 when it's infinite. And here is just the case where system envelope of AFN is actually a relative Kunz-Pimsner algebra, which in this case is actually isomorphic to a simple Kunz-Pimsner algebra.
Maybe just the Kunz algebra, ON.
Yes, Kunz algebra, yes.
The universal sister algebra generated by...
Yes. And
isometries.
And also in this case, we have that irreducible representations of Kunz algebra are one-to-one correspondence with n tuples of isometries V1 Vn, such that sum of VK dual is identity operator on Ash. It is for finite n. For infinite, we will have here an inequality less than equal. And these families rise to representations. These are representations of T of E. And also, if we have a completely positive map on bound operators of E, associated with isometric coherent representation of E, determined by this sequence, we may by this sequence we may construct an isometric coherent representation of E, and then we'll have that if psi is a completely positive map, I have discussed before then. Okay. So now we have that all irreducible representations of Kunz algebra are boundary representations for non-commutative disk algebra if n is finite. Okay, so this brings us to conclusion. Any questions?
Thank you. So, questions, please. Well, maybe I have a question just to understand better the special case of the non-commutative disk algebra. So we claim that it follows from the above results that the sister envelope of the non-commutative disk algebra is the Kunz algebra. Could you explain once again the concrete embedding
Realization.
Concrete realization. That is how we what is the map? So we must have some canonical map from the non-commutative disk algebra to the Kunz algebra. So could you repeat once again the explicit construction of this map?
I didn't construct it. The map. I just saw that there is an isomorphism.
But maybe there is some explicit form of.
Yes, but I didn't explore it yet. I don't know the explicit form.
So my conjecture was that maybe it is very naive, but how can we construct these operators V1 to Vk out of the equation operators? So we consider the algebra of bounded operators on the full Fock space, and if we quotient out the ideal of compact operators, then maybe the equation operators, the equivalence classes of the equation operators in this quotient will satisfy the relations for the Kunz algebra. So when we take that the C-star algebra generated by these elements in the quotient, we get exactly the Kunz algebra. So is that correct, or
it may be correct. I don't know yet.
Well, okay, thank you. Maybe the question was inspired by the fact that if we take the operators themselves, they don't satisfy a required relation. But it seems that they should satisfy modulo the compact operators. So when we quotient out the compact operators, we get our embedding into the Kunz algebra. Okay, thank you. More questions, please. Okay, if not, then we thank the speaker again.
Thank you.
Dima, and I think that next week our speaker will be Maria's left. So our next speaker will be Maria Shigorotsova, and she will continue her story about dynamics now in the non-commutative setting.
Thank you. Goodbye.
Thank you.